fifth generation programming languages. That at a certain point, generations don't matter anymore. You know, like how we're an iPhone generation like 16 and a half or something.
At a certain point, people are just making stuff up.
Well, people are always making stuff up. That's like all of our technology, isn't it?
Well, that's right after version 1. Version 1's like, I have a great idea, and here it is. And everything after that is like, we're just going to wing it. This is
We're just
all
going to
probably
iterate.
fine.
We'll iterate on that idea by just making things slightly faster and moderately worse.
What's the old expression? Move fast and make things completely incoherent?
Well, that is Microsoft's motto, indeed. Hello, alleged human, and welcome to the Chaos Lever podcast. My name is Ned, and I'm definitely not a robot. I'm probably also not a Microsoft MVP after that comment. Woof. With me is Chris, who is also here. Hi, Chris.
And incoherent.
Cache coherence is the most difficult thing after naming stuff. Speaking of names, we have another guest, Ivan Pepelnjak. He is a CCIE Emeritus, a BGP Titan, and a friendly human. We're very excited to have you here. Hi.
Hi. Thanks for having me.
Absolutely. So for anybody who is not familiar with you, and that's probably going to be very few people, can you give us just a quick background about yourself? We've got about 6 hours.
Okay. So where do I start? Networking engineer, developer, whatever, since mid-1980s, I think. So I just dated myself, gray beard. Worked on all sorts of crazy stuff. I was running an internet service provider in the 90s. I was the guy running the BGP courses and then OSPF and DIGRP and ISIS, so all the routing protocol staff courses for Cisco systems. If you were attending the very first version of the CCNP curriculum, those were the courses that we were developing. Probably set up like the second remote lab system worldwide for routers. The first one was Terry Slattery with Mentor Labs, and we were like close behind.
Gotcha. Oh,
then semi-retired, then got back, started my own company, started blogging, doing webinars, bitching about the state of networking, which isn't hard these days. Semi-retired again. Now I'm working on an open source project that should make networking labs suck less.
Oh, I am all for that. I recall studying for the CCNA and then the CCNP and, trying to use the emulators of the time. This was the early 2000s. And it was a little rough, if I'm going to be
Emphasis
honest.
on the word trying.
You're so diplomatic. You definitely wouldn't be suitable for Trump administration.
It's true for so many reasons, but yes. So I'm glad to hear that improvements are being made. Maybe someday I'll actually try to get that CCNP again. Unlikely.
Nope. No, if anyone wants to go for any certification on that level today, it should be something cloud related.
Is there a certification that you would particularly recommend for people getting started?
I have no idea.
Yeah, just something cloud related.
Yeah.
No, that does seem to be the general consensus that I'm hearing. But let's dial back. Let's go back to an earlier time. I'm not going to say a simpler time because I don't think it was simpler, but an earlier time.
It was different.
Yeah. Oh, so what I wanted to talk to you about, because I think you have some strong opinions on this, is the history of NAT, or Network Address Translation.
You must hate me.
It was a necessary evil, maybe, that arose sometime in the 90s. And I could be wrong about that. So, Ivan, please correct me. But it is responsible for the implementation of the internet as we know it. So could you just help set the stage for what would eventually become NAT?
Okay. So do I start with long, long time ago on a planet far, far away?
Possibly.
There were networks. Anyway, in those days, IP was just one of the many options. It wasn't even the best option. It was some crazy academic project that no one was taking seriously.
Hmm.
And every enterprise vendor had their own stuff. IBM had their own stuff. DEC had their own stuff. HP had their own stuff. Who else? Siemens. There was this French company that was also making Unix-like systems. Can't remember what it is. And then there was Banyan Vines and Apollo and AppleTalk. Of course, Apple had to do things differently.
Oh, I
Did
remember
I
Apple
mention
Talk.
Novell Network? That was the initial guerrilla product that then started spreading like fungus across enterprise networks and, killed all the joy in the networking engineers because it was so crappy. Anyway.
If I remember correctly, Novell used IPX as
Yes.
its protocol.
Yeah.
I don't know anything about it. I just know that
No,
would pop up
the
in menus.
real problem. So Novell actually had some great ideas like automatically assigning network addresses based on MAC addresses
Hmm.
that we got later in IPv6 because they were so jealous that someone else has it, but they don't. And we can get into that if you wish. The problem with Novell was that all servers were routers. So all the traffic was going through the servers and burning CPU cycles to forward packets that, the CPU cycle should really be spent on serving files. A file server is, after all, a file server, not a router.
Right.
And the other problem was that they had this service advertisement protocol, which is something like Bonjour is today in Apple networks, where everyone is telling everyone else what services they have. And those things were collected by all the servers and re-advertised in all other segments by every server every 30 seconds or so. And you have to keep in mind that in those days, 64 kilobits was a fast link.
Wow. So they were
2 megabits was bloody expensive. And
So
now
this was a little
imagine
bit of
having a 64 kilobit link and half of the bandwidth is used
Right.
by service advertisements. You hate that stuff by definition.
That reminds me a little bit of how early Microsoft networking would also do something similar with
Well, with
whatever
NetBIOS, yeah.
NetBUI, I think it was.
NetBIOS was the original one. It was running on straight on Ethernet, and NetBUI was, that brings us to this topic, NetBIOS over IP. Thank you.
Oh, I did something.
So, in late 80s, the writing was on the wall. People will use IP. And so enterprises started planning for that. They might still, have everything on Novell or Microsoft or DECnet or IBM stuff or whatever, but they knew that eventually this IP stuff is obviously winning. This OSI stuff is not going anywhere because these IP guys are actually doing something, and those OSI guys are meeting every 2 or 4 years at exotic locations and wasting everyone's money. So the enterprises started thinking really hard about what to do. And the first thing you do is you grab part of the address space, which in the good old days was just sending an email to some guy somewhere in US who had a text file, not even an Excel spreadsheet. And that guy would look into that text file and add you to that text file and send back an email saying, this is yours. And that was it. The next problem we had in those days was that there was no prefixes in networks. So, today we look at the IPv4 or IPv6 address and we say the left bits are the prefix, the right bits are the host bits.
Mm-hmm.
And the boundary can't be anywhere. In those days, the boundary could be at the first byte, at the second, so that would be class A network, at the second byte, which would be class B network, or at the third byte, which would be class C network. And the class of the network was coded in the first 3 bits. So anything from 0 to 128 is class A. And by the way, the last class A is 127.0.0.0/8, which everyone should be familiar with.
Yeah. Though I have to admit, I only ever use the very first host in that /8. Kind of seems like a
You
little
know
wasteful.
what? You know why you need all the others? For something like vagrant UDP tunnels. So if you want to build in KVM a UDP tunnel between 2 VMs on, 2 VM NICs on your server, then you have to send UDP packets from some IP address to some other IP address. And luckily, we have 16 million of IP addresses in the loopback subnet. So you never run out of the IP addresses for the UDP tunnels between the VMs, because if you ever manage to run 16 million VMs on your server, let me know.
I will work on that. Get back
I
to you.
believe you. Anyway, because of that, people had to grab the next bigger thing that would fit their needs. So enterprises were typically going for class B. Some people managed to grab class A, like Stanford or DEC or Xerox or MIT, I think. Department of Defense, obviously. And so it was pretty obvious in the 80s that we will be running out of the IP address space if things, will keep going like that. We were pretty far from the cliff, but it was obvious that there is a cliff and that we will have more than 30 mainframes in the world, as IBM once claimed. You remember those things, right?
Yeah, we
The
did a
IBM
whole
CEO
episode on
saying, well, we'll
mainframes.
never sell more than 30 of these things. And
Yeah.
Bill Gates supposedly saying no one ever needs more than 640K of RAM.
Yeah, those predictions are adorable.
Yeah.
Was there any concept of just how big the public internet was going to get at that point?
No.
Because I mean, yeah, I was going to say.
This was pre-web.
Right.
The
So,
internet exploded with web.
mhm.
This was still, enterprises and enthusiasts and academics and computer vendors. But the enterprises were seeing the writing on the wall and they were getting ready. If nothing else, there was email. So, very early, let's say late 80s, early 90s, people who could foresee, who could extrapolate curves, let's put it this way, were pretty sure what is going to happen. And people started thinking what they could do, because it was obvious we would need bigger addresses. And so there was a proposal, and I found the dates in 1992. Someone wrote an RFC, this is RFC 1347, where they said, well, let's just run TCP and UDP over CLNS, the OSI stuff. The OSI addresses are variable length, and the minimum length is something like 10 bytes or something. So, no problem. We can squeeze anything you wish in there. And there were people implementing that stuff almost immediately, because router vendors already had the OSI stack, because the transport gear, the SONET and the SDH gear, was managed through the OSI stack. So if you wanted to build a management network for a service provider, you had to support that stuff. So it was there. It was in the code. It was in Unix networking stacks because people were using Unix systems to manage those networks. So all the major vendors had something, and Digital was betting the next generation of DECnet on that. Stuff was around. And it would be trivial. We would just roll it out, and in a few years, we would have a running product and problem solved.
So just to clarify, CLNP would be a replacement for IP.
For IP, yes.
So this isn't a bolt-on to alter IP in any way. It's
No.
totally separate
This is
protocol.
like IPv6 is replacement for IPv4 with TCP and UDP running on IPv6. This would
Okay.
be CLNP replacement for IPv4 with TCP and UDP running on CLNP.
I'm going to assume, because I'm not familiar with CLNP, that it didn't take off.
There was this famous high-level IETF meeting somewhere in Japan that no one wants to talk about. You can't find anything about it on the web apart from certain mentions of the Kobe incident. I think it's Kobe incident. I found a small book. I think it's The Elements of Networking Style. I'll send you the ISBN. It's not digital. You have to buy a hard copy. It's from a guy that was on the IP side of the world, but it's an interesting book. It gives you the mindset in those days. So anyway, there was this meeting, and they said, "Yeah, this makes sense. Let's move ahead. This is how we should do things." And then they had the grassroots revolt of the Make IP Great Again folks. And they said, "No, we will not take anything from the enemy. We don't care if that thing works. We don't care if it's okay. It's the enemy. We will not take anything from the enemy. We will develop our own stuff." Now, let me give you the timeline. That proposal to run TCP and UDP over CLNP was made in 1992. And I'm pretty sure the production code was in Cisco iOS release in January 1994. IETF got their act together in June 1994, when someone managed to publish the first draft of the technical criteria for choosing IP the next generation. So 2 years after we had a solution, IETF finally decided they need some set of requirements. And then in September 94, and the final RFC was published in January 95, they produced, based on those requirements, the recommendation for the IP next generation protocol, where they took 3 different ideas, slightly mixed and matched them, because that always works so well in committees. That's how we got 48-byte ATM cells. Not 32, not 64, 48. And this was the start of the IPv6 development process. And then, instead of just saying, we'll replace 32-bit addresses with... initially, the proposal was, let's replace the 32-bit addresses with 64-bit addresses.
Okay.
And then someone said, no, let's make it 128-bit, so we will be as cool as Novell.
All right.
Because the first 64 bits will be the prefix, and the second 64 bits will be the MAC address.
That's where the 128 came from. They wanted to use the MAC address for...
Yeah.
Okay.
Of course, in those days, they didn't realize that because nothing was portable in those days. There were no laptops.
Right.
They didn't realize that if you always put your MAC address in the lower part of the IPv6 address, we don't need tracking cookies or anything else. We can just track you based on the MAC address.
Right.
which is why we have now so many privacy-enhanced IPv6 addresses. And we change them every time you power on your iPhone or iPad. It gets a different address.
So despite the idea being that it would be linked to your MAC address, that's ultimately not how we chose to implement it.
Well, we implemented that, and then a decade or two later, we had an oh shit moment. And that's the whole story of IPv6 in a nutshell. People came with all these academic ideas, like, infinite extension headers, and extension headers that would be looked at on every router along the way, and extension headers that the routers could change along the way, and, all sorts of crazy ideas. And all that got baked into IPv6, and that, of course, made it somewhat hard to implement.
Yeah, you're talking 1994, and I'm trying to think about the hardware of that
Yeah.
era. Being able to
Well,
process a 128-bit
hardware
address.
guys were pretty smart in those days. Cisco already had a prefix-based forwarding implemented in, I think, FPGAs. And it worked for IPv4 and CLNS and later for IPv6. But, the infinite extension headers, that obviously doesn't fly. And the moment you want to do any filtering on TCP or UDP port numbers, and I can just shift TCP or UDP port numbers anywhere in the packet, good luck. So, of course, the academics thought that, you could obfuscate the TCP port numbers, and so people wouldn't be able to filter you anymore. Now, I would use an undiplomatic word, but I won't. The people in the middle just said, we don't care about your obfuscation attempts. We'll just drop your packets. So, of course, those ideas never worked. They do work great for the bad guys. It took the industry a decade or so to implement a proper router advertisement guard. Because, you don't want anyone to just say, I'm the router, send the packets to me.
Right.
But that's how IPv6 works. And so they said, well, no, we will implement some filter in the switches that if, the router advertisement comes from the untrusted port, we'll kill it. And then along comes Fernando Gont, that's a security researcher focusing on IPv6, saying, if I add an extension header, you won't see this is a router advertisement, but the host will.
Sneaky.
And then they go like, okay, we can fix that. And he goes like, yeah, but not if I fragment. We can fix that. But not if I overlap the fragments. So the whole IPv6, is so-called second system effect. You build something first and it's crap, like IPv4 was crap before DHCP and classless routing and all that. And now you get the opportunity to do it again, and you create the most bloated thing the earth has ever seen, because you want to fix every error and insert every great idea you ever had without testing it out in reality. By the way, people should look up the second system effect on Wikipedia. It comes from a book by a guy who was the manager of operating system development for IBM mainframes, and he experienced that firsthand. And on the Wikipedia page, IPv6 deployment is quoted as an example of the second system effect. So we got an overbloated protocol full of academic ideas, not implemented anywhere, not tested anywhere, and we were running out of IPv4 addresses.
Right.
So a few people, practical engineers said, gee, we are giving Class Bs to Siemens and Coca-Cola and Pepsi and who knows what else. And those guys are never going to use those addresses because they're not crazy enough to connect their hosts directly to the public internet.
Mm-hmm.
They will just number their hosts internally, and they don't really need public addresses for that. What if we would assign network 10 for private addresses? And that was started in March 1994. That was the first RFC saying, let's use network 10.
Okay.
And immediately after that, there was a counter RFC from the rich guys who believed in religious purity, saying, no, we shouldn't do that because we will kill the end-to-end connectivity. Now, those guys were coming from Apple, SGI, and Sun. And guess what? Those companies had tons of IP addresses because they grabbed them in the initial rush. So obviously, it was easy for them to say, no, you couldn't use network 10. That would be, so offensive. Anyway, RFC 1918 eventually happened. And the other thing you have to understand is that in those days, nobody was planning to use direct end-to-end connectivity between the clients. Even today, honestly, why do you need direct connectivity between the clients? It's just for the voice calls, or well, now it's video calls and BitTorrent. Everything else is client-server.
Right.
Which means that having clients with global addresses reachable through the public internet is plain stupid and security risk. And people understood it in those days. And everyone was building their networks with a sandwich. So the way we were building firewalls in the good old days was 2 routers with a proxy server in the middle. You would have packet filters on the 2 routers. So inside would only be allowed to connect to the proxy server. The proxy server could only open connections to the outside world, not to the inside. And every application protocol would be proxied.
Mm-hmm.
And that allowed people to use network 10 internally and then have a /24 class C because you couldn't get a smaller prefix for the DMZ, for the proxy server and the 2 routers. And then the proxy server would connect to the internet. Problem solved. You can be, I don't know, Coca-Cola worldwide, and you would only need a Class C network to connect the whole enterprise organization to the global internet. Well, maybe with regional exit points, but let's not go there. The only problem with that was that you had this application proxy in the middle.
Mm-hmm.
So, web worked well, FTP worked well, email worked well, but you wanted to deploy a new protocol. It didn't go through. So someone had this great idea saying, yeah, but if I look at did you ever work, by the way, with the old telephone exchanges?
Oh, geez.
Where you would have one phone number for the whole organization, and everyone calling out would appear to be coming from the same phone number.
Yeah.
And then you would have some extension for direct in-dialing, where if you would know the extension number, you could dial in and get to a certain person.
Yeah, I remember I was working on a phone system. It was one of my first jobs, and they were talking about DIDs, and I was like, what's DID?
Yeah, exactly.
I'd never heard that acronym before, and then the guy explained to me, he's like, people who get DIDs, you can direct dial them. from the outside. Everybody else, you have to dial the main number and then their extension.
And that was the exact same situation with the early internet access. There were a few people who had special applications and they would need direct access to the internet.
Mhm.
And everyone else was just using email and web. For those few people, you just assigned them IP addresses from the DMZ, but they were inside. So you had to translate the inside addresses into DMZ addresses so that they could get to the outside world. And voila, we have NAT. It
Sounds so
was
simple.
initially used really just for the exceptions. Those few people who needed direct internet connectivity from an organization, that they couldn't use the proxy servers, then would use NAT. And then of course, once you invent something like that, and by the way, NAT was documented as an RFC in 1993. So NAT is older than the private address space and way older than IPv6. Because, we were solving a different problem. It just so happened that this tool could also solve the lack of IPv4 addresses because of the IPv6 blunder.
Mm-hmm.
And so, when you have the tool, when you have a hammer, everything starts looking like a nail. So the next thing that happened was that people said, well, you know what? We have NAT. Can we just skip the proxy server, please? Because, it's faster if you go direct. Links were becoming faster, and the proxy server was becoming a bottleneck.
Mm-hmm.
So it was like, yeah, let's say I get 4 class Cs, so I'll have 1,000 addresses and I'll share them across people who want to go to the internet. There will never be more than 1,000 people. And you will, get an IP address when you start using it. And when you stop using it, it will time out and someone else will grab it. As you can imagine, that didn't end well.
Right. We severely
So someone
underestimated.
smart said, you know what? What if we would mux multiple people into the same IP address and use different TCP and UDP port numbers? Because in theory, a host can open 64,000 TCP or UDP sessions to one IP address. So it can open millions of sessions to different IP addresses. What if we would be really smart and reuse the IP address with different TCP UDP port numbers? And so we could squeeze more than one person through one IP address. And so the NAT as we know it today was born. And then, obviously, the residential internet started. We were all using dial-up over the phone lines with the squeaky modems. You ever use that modem when you could hear the modem sound when you dialed in?
Oh, yeah.
Oh, yeah.
For sure.
So, those days. And that was okay. You got your IP address when you dialed in, and then when you disconnected, you lost your IP address and someone else would get the IP address. And from the service provider perspective, you needed one IP address per modem, not per user.
Mm-hmm. Or
That was
concurrent
manageable.
user. Yeah.
Until DSL came along. The always on internet connectivity for the masses.
Right.
There, you had to assign one IP address per customer, which was still okay. So as long as you were connecting your PC to your DSL modem, that was good. But then Wi-Fi came along. And all of a sudden, people wanted to connect multiple devices from the home to the internet.
Mm-hmm.
But nobody would give you more than one IP address for the same amount of money. Why should they? But gee, we have this hammer and this looks like a nail, so let's use it. And that's why everyone today is using NAT to access the internet.
That's
Apart from the mobile phones of the operators that were early enough in the game that they grabbed enough IP addresses. So, for example, I know that Telecom Italia has every phone on a global IP address.
and that's
Because, Italian population is not growing. They reached the peak penetration of mobile users. No one has more than one phone active at the same time. Apart from certain people that have to use burner phones, but let's hope they are minority even in Italy. And so they grabbed enough IP addresses early on, and they can afford that. Whereas all the new operators, they were late to the game. They can barely get some IP addresses, or they have to buy them. So all the new operators are forced to use so-called carrier-grade NAT. In the good old days, a customer would get one IP address. And then you would use NAT in your home on your Wi-Fi to connect 20 devices. Today, in many cases, there's another layer of NAT inside the service provider. So a customer is not getting one IP address. A customer is getting maybe a portion of one IP address, maybe 1,000 ports of that IP address. And that's why the mobile operators are so keen to move to IPv6.
right. I'm thinking about the carrier grade NAT, and then I'm thinking about the number of devices I have in my house. And if I multiply that out to all the houses around me, having a fraction of an IP address doesn't work anymore. I need more than that.
Well, effectively, you get something like 1,000 ports. Or maybe you get 4,000 ports.
That's still
But
close.
no, remember that you can reuse the same. If your NAT device is smart, it can reuse the same port for different destination IP addresses.
Oh, okay.
So as long as you're going to Apple and AWS and Netflix and Cloudflare, you're good. If everything is behind Cloudflare, you have a problem.
Right. And they're using unicast. So
yeah, it's all unicast these days. Multicast is used in scenarios like video surveillance networks, where multiple people can watch the same video camera, and they're using multicast because the camera cannot produce more than one feed.
mm-hmm.
Or it's used internally in the service provider networks for the direct IPTV, the live stuff. The moment you get into replay mode, or you want to skip something, or you want to go back 5 minutes, or you're on any streaming service, it's all unicast. And the other big user of multicast are the stock exchanges. Stockfeed is sending out as multicast so that every broker receives it at the same time.
Right. Instead of giving one an advantage over the other.
There were even stock exchanges where they measured the fiber cables so that every broker had the fiber cable of exactly the same length.
It matters.
Yeah, it matters.
So, we got the story of NAT now where it became necessary for a number of different reasons. But as you mentioned, the carriers are switching to IPv6 for a lot of what they're doing. Are they still using NAT in any way? Or if once you make the jump to IPv6, does that remove the need to run NAT?
Unfortunately, not, because so much of the content is still on IPv4.
Ah, okay.
So, as long as there is some content on IPv4, and if you're a service provider, you want to avoid the support calls. And if there is more than one service provider in a certain town, which I'm told is not the case in US sometimes,
Sometimes.
but in Europe, we do have a freedom of choice. If one of them would be blocking access to IPv4 sites, you know what will happen? Everyone will go to the other one.
Mm-hmm.
So you can't afford not to run NAT. What they're trying to do, though, is to avoid the bandwidth going through NAT as much as possible, because that's costing you. The CGM box is expensive. Terabit of netted traffic is bloody expensive. So if they can push as much traffic over to IPv6 as possible, they are making more profit.
So that's
And
what's truly
that's
going to drive IPv6 adoption
yeah,
is the
and
money.
that's why you have Facebook and YouTube and Netflix and all the video streaming on IPv6. Because it's in everyone's interest that it's on IPv6. Because if it would be on IPv4, then some users would go through carrier grade NAT and their performance would suck. So if Netflix works great for me and Disney doesn't, guess what? I will cancel one of those services.
Not if you have little kids. Ask me how I know.
Yeah. Yeah. We went into Disney Plus for Star Wars.
So, looking towards the future, is there going to be a time where we abandon NAT at all levels? And
No.
no? Okay.
No. So we will not. So if we all go to IPv6, which, we will all switch from COBOL to what, Python in what year?
Never.
Exactly. So when we all switch to IPv6, then theoretically we will never use NAT again. Unfortunately, that's not true. Even in pure IPv6 world, there are two cases where you absolutely need NAT. One is load balancers. Load balancer presents one IP address on the outside and distributes that IP address to many IP addresses on the inside.
Mm-hmm.
How do you think it does that?
Well, I know.
Yeah, it's NAT.
Right.
There's no way around it. I mean, okay, technically it can be a TCP proxy or it can be a NAT device. TCP proxy is slower than NAT, so guess what's implemented?
Right.
The other issue is if I want to have two uplinks from my home. So I want to have a connection to, I don't know, I'm making this up, T-Mobile or Verizon and Comcast for redundancy reasons. We are all working from home and some of us are making money with that. And if your internet link is down, you have a problem. You can't do everything from the coffee shop.
Mm-hmm.
So you want to have two uplinks. And the small sites of serious companies have the same problem. So, for example, I was once speaking with a networking architect from probably Fortune 100 company. And he said he has tens of thousands of stores worldwide. And each one of them has to have redundant internet connectivity.
Mhm.
We knew about this problem since 1990s. How much do you think we did to solve it in the meantime?
I'm
Apart
suspecting not
from
a lot.
academic ideas don't count.
Okay.
Nada.
Ouch.
An RFC was published a few months ago, yet again describing the issues with multiple uplinks. Issues, not solutions. This was the requirement document. IPv6 is old enough, it can get drunk in US. And we are still writing requirement documents for multi-homing solutions.
What you're saying is that NAT isn't going anywhere, and we
Yeah.
might as well get used to it.
Yeah, because the only way to solve multi-homing in IPv6 today is with NAT. You get two prefixes from two service providers. You have inside addresses, whatever they are, and then based on the uplink you decide to use, you change your source IP address into the prefix that the service provider likes. Otherwise, the return traffic is never coming back.
Right. Well, this has been a fascinating journey through the world of NAT, and I want to take a moment and thank you, Ivan, for sharing your wealth of knowledge and history in this topic. If people want to know more about you, I know you said you're semi-retired, but you have this open source thing. Is there anything you want to promote or point people towards?
Well, so there are like 3 or 4 things.
Okay.
If for general networking, ipspace.net. Blog.ipspace.net is still regularly updated. There are tons of webinars on the website, and although you can't buy them anymore, I'm making more and more of them public. So, people who never had account on my server can just watch those. For the networking labs, it's netlab.tools. Tons of documentation. It's an open source project, so anyone can contribute. And I love people who appear out of the blue sky, never heard about them, with a PR saying, oh, this doesn't work. This is how I fixed it. Can we merge this? Like, sure. Cool, dude. Thank you. And the last thing, if you want to learn more about BGP or ISIS, I use that tool to create tons of labs for BGP. I think it's like 40 different labs exploring different BGP features.
Wow.
And it's all set up with NetLab. So you just download the repository and you install NetLab and you're good to go. Or you can run the labs for free in GitHub Codespaces.
Very cool. All right. Well, we will include links to all of that in the show notes.
Thank you.
Ivan, thank you once again for being a guest today on Chaos Lever. And hey, listeners, thanks for listening or something. I guess you found it worthwhile enough if you made it all the way to the end. So congratulations to you, friend. You accomplished something today. Now you can go sit on the couch, fire up 2 different routers, and set up NAT for your internet connection. You have earned it. You can find more about the show by visiting our LinkedIn page. Just search Chaos Lever or go to our website, chaoslever.com, where you'll find show notes, blog posts, and general tomfoolery. We'll be back next week to see what fresh hell is upon us. Ta-ta for now.